Oh, thank you, Ilana, and thank you everyone for joining. And yeah, I think we'll be expecting a few more people still, but thank you all for joining, and we hope this webinar will be beneficial not only to yourself but also to your companies in the future. And yes, on the agenda today, we will begin with a bit of background on underground communication systems overview, a bit of theory, and to help everyone better understand how underground communication works. Thereafter, we will give a few examples and case studies to see the implementation thereof. And just to wrap everything up, we will just give a brief overview of the vast products Poynting offers for underground communication and also for tunnel communication. Thank you, Steve. Stephen, you're muted.
Sorry for that. the common phrase for 2020. So I just want to also mention that the presentation would be, or this webinar would be quite technical, but there's also some interesting business cases just to put it all into context. So if you can bear with us. Good.
So we'll begin with underground communication systems overview, and yes, I think Peter will discuss this as he has plenty of years of experience in that field.
Okay, my slide. What we have found as far as communication underground is concerned, that there are three main areas where we touch the communication, and health and safety, as you know, that is extremely important. Production rate and production recovery. Now you'll see that we tick all the boxes as far as that is concerned. Network availability, that's extremely important for health and safety. RF stability, costs, and configuration control. Production rate, of course, that's where cost becomes, of course, very important. Balancing your OPEX and your CAPEX. And then configuration control is extremely important in both health and safety and production rate. And then with production recovery, costs, of course, are extremely important as well. All of these, as you can see below, are mission critical. Thanks.
Yes, maybe, and just a comment from my side, Peter, is that from especially in the mining industry, that availability of your communication networks is obviously mission critical, and it is so important in an industrial environment to have and ensure that you have stability, that you have link availability, and the best performance possible. So just another comment from my side is that although we're touching on mining quite a lot in this presentation or this webinar, it's covering underground communication, whether that is for automotive tunnels or for metro tunnels. So it's covering all of those different topics, but we will be focusing on mine. All of what we mention on the antennas and the technologies apply to all of them. But because we have more experience in the mining industry, the webinar is focused a little bit more on the mining side. Good. Circular versus linear polarization. This is just quite an important aspect just to mention to you. We've seen quite a few customers use linear antennas in mines, and so just a term that I like to use is courses for horses. And for those who understand that, because I understand it's a British term, is that what happens in mining is a lot of people use normal linear antennas, and although the majority of the antennas that we do provide are linear antennas and they are quite good, in tunnel environments, circular polarized antennas just work so much better, and I'll explain exactly why that happens. So firstly, when you have a linear antenna, as you can see on the left-hand side over here, this antenna over here, it's an upright antenna, which means it's a linear antenna. You can see that this thing, because it's mounted vertically upright, it transmits a sine wave which is in alignment with the antenna. So you've probably seen on television antennas that when you have a Yagi installed, it's either mounted upright or horizontally. And it is so important when you install an antenna like this that when you have the one side vertically installed, then the other side, the receive side, also needs to be vertically installed. as with the television antennas, when you have horizontally installed antenna, then the other side must also be horizontally installed. So what I'm trying to say with this specific slide is that when you transmit, especially in a mining tunnel, a signal which is linear, and it is a sine wave, either vertical or horizontal, but in this case vertical, it may reflect, bounce off the walls, and on the other side received at a different polarization. And when a signal is received at a different polarization, the full amplitude of the signal isn't received on the other side. So in other words, you have deterioration of your signal. So because in mining tunnels, the signal rotates unpredictably, linear antennas are not always the best option. The same with metro tunnels, the same with automotive tunnels. So in those cases, it is so much better to use a circular polarized antenna. So obviously in tunnels, the propagation is affected by the tunnel dimensions, surfaces, but we'll get to that shortly. On the circular polarization, as you can see over here, as the signal rotates, as it is transmitted, it actually contains all the polarizations. So if something's reflected off the wall and it is received, it isn't constrained to a linear situation like this. And so it just makes or provides much more reliable links. It's also as if the propagation adapts to the environment and to the tunnel dimensions. And the tunnel often acts like a waveguide for this type of circular polarized antennas. And then also quite interesting, and I'll show that in a case study shortly, is that circular polarization tends to propagate past obstacles and obstructions. So I'll just quickly touch on that in the case studies where that has become quite evident and what the results of that is. Good. So just another slide on vertical and horizontal polarization. As you can see over here with the vertical polarization, you've all probably learned in science in high school that when you have a wave, also in a water situation, you drop two stones, you'll see that there's constructive and destructive waves. And as soon as a wave like this bounces off the top and the bottom walls of the or surfaces of the tunnel, then you'll, after the first reflection, you'll start receiving either a constructive or destructive wave. What unfortunately happens is you could have an amplification of your signal, but you could also have a deterioration in your signal. What actually happens is an effect which is called fading. So the signal fades and becomes unpredictable. So you can either have a very strong signal or a very poor signal. And most of you have probably, especially in the older days when normal FM broadcasts and AM broadcasts on your car radio was a little bit more sparse, you've probably seen when you approach a traffic light that when you stop, all of a sudden your signal goes away. And then you just move forward maybe 1 meter, 2 meters, and you'll see suddenly your signal pops back again. And that is because of this phenomena. And this is quite common in all different types of communication. But it becomes quite prevalent in tunnels, mining tunnels, automotive tunnels, and so on. Same with horizontal polarization. Ernst will mention now about a study that was done about this, but the same effect happens. It bounces off the sidewalls. Circular polarization is a little bit different. Because of its circular nature, it tends to, when it bounces off the wall, it changes the polarization of the signal, and you have a mirror effect. So because you're transmitting a circle, imagine these, I don't know what you call these springs that you have that you send down the steps, but it changes the, so if the spring was, went down the first step in one way, it goes down and it changes and gets a mirror effect. And that causes the signals not to fade that much as with linear polarization. Good. Next slide is just to show you that you also have within circular polarization, you have both left and right polarization. So many circular polarized antennas are either the left or the right. So it's just something interesting to take care of when you select your antennas. But we'll get to that point also shortly. Good. You'll also see here that the way that the signal reflects off the different surfaces just becomes much more manageable. But the polarization does change every time it reflects off the floor. Good. Characteristics over here, Ernst is just going to give us a little bit of an overview. Study that was done actually in the 1970s. And it is a reference case still today and still valid today, which is quite interesting. Ernst?
Yes, thank you, Stephen. So this is just to explain the characteristics of underground communication. And as you can see, this has the study the propagation of electromagnetic waves down tunnels have been studied for quite some time. And this IEEE article was published on June of 1978, and the title was Radio Communications in Tunnels. Now, this study was done in Japan in a train tunnel, but the theory and the results was still portrayed to mining and underground tunnels. Now, as you can see on the right, you have your graph, and this is a attenuation graph. So on your y-axis, you have your attenuation constant is a dB per kilometer in a logarithmic scale, and then on the x-axis at the bottom, you have your frequency, which is also in a logarithmic scale. So the study found that the lower your frequency, the more attenuation your propagating wave will experience. So for instance, for LoRa at approximately 900 megahertz, you'll experience 2 dBs per kilometer. But let's say you move all the way to 2.4 gigahertz, you get an attenuation of approximately 0.4 dBs per kilometer, so which is significantly reduced. And if you move up all the way to 5.8 gigahertz in the Wi-Fi band, it's 0.1. So it has significantly reduced, and that's why it's much better to use higher operating frequency bands in tunnels as they experience least attenuation. And the study also indicated that underground tunnels acts like circular waveguides. So that's why circular polarized antennas work so perfectly well in tunnels or underground communication.
Just something to mention there, Ernst, is that this was done in a tunnel with very smooth edges. And I think that leads us to the next slide, which gives us a little bit more information on that.
Yeah, just to illustrate the theory of the article, we just have this representation of a tunnel. Now, as you can see, this tunnel goes from, this is just an illustration from 900 megs all the way to 7.2 gigahertz. Now, at 900 megs at LoRa, you can see the tunnel is quite rough, and the propagating signal would be attenuated due to the roughness of the walls, and yeah, as it would also reflect quite rigorously from the underground walls, the roughness of the walls. But if you move all the way to 5 gigahertz, you can see that the roughness of the walls significantly decreases and it's much smoother. That is why as it's smoother, the propagation of the waves will be much better and can travel much further, which is in the contrary to normal wave propagation outside.
So in other words, on 5 gigahertz, we found that is a little bit more suited to smoother tunnels, tunnel walls, whereas the lower frequencies are a little bit more suited to rougher tunnel walls. And that's just because of the wavelength of the signal that is affected by the roughness or the smoothness. And the smoothness, as we said, acts more like a waveguide for a specific frequency band. And the roughness works a little bit better for lower frequency bands. So this is quite interesting when one selects your frequency band for the specific tunnel that you are using. However, we have actually seen quite different results, and we'll get to our case study soon just to show you what effects the different frequencies have on the different type of tunnels.
That is correct. Thank you, Stephen. And at Poynting, we also offer antennas for every frequency from 900 megs all the way to 7.2. But we will give a product overview at the end of the presentation to give you a better understanding of what we have to offer at Poynting.
Good. Thank you. Thank you, Ernst. I'm not sure if I skipped a slide there. No. So just a few implementation scenarios just to show you. We've used a generic router over here. This is our Heli-22, which we will get to the overview later of the antennas, but just to show you how circular polarized antennas work, at least how to configure them. So on the specific Heli-22, it's quite a unique antenna. I haven't seen anything else in the market like this. We do have some competitors on some of our other ranges, but we haven't seen something that is dual band firstly per antenna or multi-band. So as I said, we have an antenna that, or actually Ernst mentioned that we have an antenna that goes from 1.7 gigs all the way to 7.2 gigs for Wi-Fi 6, that is 802.11 what's it, AX, and also for 5G, LTE and 5G. But this specific antenna that we're showing over here, Heli-22, is based on the ISM frequency bands, which is used in Wi-Fi, that is 2.4 and 5 gigahertz. And so when I say 5 gigahertz, I actually mean that it goes all the way from 5 to 6 gigahertz. That's just the band. And just to show over here, because a lot of our customers are not sure how to connect them and how they are configured, but just to show that the one antenna is set up to be left-hand circular polarized. And if you remember the previous slides, I've shown left and right-hand circular polarization, but we'll also give a little bit more information on that soon. But the first antenna, so this is actually an antenna assembly that we sell as the Heli-22, which is physically got two bidirectional antennas. Each antenna radiates in both directions. So you don't need to connect two routers or two access points or nodes or radios to this unit. It already splits the signal in both directions. So you would have transmission in one direction and the other direction, perfectly suited for tunnels. So if you install this in a normal automotive or mining tunnel, you would actually propagate both ways down the tunnel, which makes it a little bit more effective. The one antenna, as you can see over here, is left-hand polarized, and the other one is right-hand polarized. So I'll just give a little bit more information on that as well. The bracketry and all the accessories that we have outside of the antenna radar, it's all stainless steel 316. Just for information, we use marine grade stainless steel for underground environments because we do know that there's a lot of chemical and salts and let's say water and so on that could corrode the metal. So we use the highest grade for this type of application. Just indicating over here is a generic router. I know that there's some routers that are connected differently, for example 2.4 here and 2.4 over there, but just for this example, just to show you that how one connects these antennas is each antenna on this assembly has two ports. The one is a 2.4 gig port, as you can see over there, and the other port is a 5 gigahertz port. So by using this, the 2.4 and 5 on the one antenna, left-hand circular polarized, and 2.4 and 5 on the other antenna, right-hand circular polarized, provides MIMO and diversity across the two antennas. So whereas I know some customers do use, let's say, an antenna in, so splitting their MIMO in both directions, which is perfectly fine, but just to indicate that this antenna offers actually MIMO in both directions, which is quite nice. Good. The same, not to go through this one too much, but the same with our Heli-21 antenna, which is a directional antenna, and this is typically mounted on the let's say, the beginning of the tunnel or the end of the tunnel, or where you have a T-junction, also connected in the same way. Both antennas have both 2.4 and 5, and then you have the left and right hand polarized. Just to mention quickly, this bracket that we have over here is, this is just one of our brackets. It is a roof mount bracket, and we also have one that is roof bolt for mining, where they have these roof or ceiling bolts that mounts directly to that. It's got a small platform over here for generic routers, so quite a lot of routers, IPs, radios, nodes can actually connect directly to this, and it just makes installation easier. All that this needs is, if this is a mesh node, it just needs power, or if it is let's say being sourced by an Ethernet connector, then it's just a power over Ethernet. So that's all you have to take to this antenna, and you don't need all the other power supplies and also have the routers and IPs mounted in a different place with long feeder cables. The shorter feeder cables also help quite a lot to reduce the attenuation, improves the throughput and signal quality. Good. Next slide over here. Pieter, you are just going to go over this one.
Yes. So this is a case in point where we've seen deployment of access points underground. Now, with access points, as you can see there, these are vertically polarized antennas. But what we did find was that these needed to be in excuse me, in distance of about 100 meters apart, just to get the signal propagation properly along the tunnel. So if you can go to the next slide, Stephen.
Yeah, so now it's just the, yes, the, let's say the case study or the business case.
Yeah, so assuming that we are going to deploy these routers over 5 kilometers, you can see the calculations there, the router or radio, the antenna and the installation, and that gets you roughly to around $230,000. I must say those are generic numbers, so you can plug in your own numbers to give you an indication of what this cost will be. Okay, next slide, Stephen.
Yes, just to mention something quickly on this also is that we've also seen, okay, so it can be 150 meters. We've also seen 100 meters, 150 meters apart. But it seems like the deployments with these linear antennas are very limited. And it just means so many more access points. So I'll just quickly go to the next slide.
Yep. So this will be the deployment that we would suggest to the client. You can see there that we quite comfortably do 400 meters, which we were spanning in the previous slide. So your cost will come down to the next one, Stephen. So there you can see that to cover 5 kilometers, we will need 13 of these access points, these stations, so to speak, with the antenna costs. So we're looking there at around $67,600 thereabouts dollars. So if we compare that to the previous slide, you'll see that that is more than 3 times more to cover the same distance. So obviously with circular, you're getting better bang for your buck.
Yes, and just to mention over here that the 400 meters that is used over here is a specific case that we've had. We've had much farther distances that we have achieved in the coverage. So, but this is just a case study, and but we have achieved distances of 500, 600, and beyond. And just to mention that these distances quoted, they're very specific to the tunnel. You could have wider tunnels, thinner tunnels, rougher, smoother surfaces, depending on what frequency band you are using. So because customers always ask us, what is that distance that we should mount these antennas apart? My first comment to them is that it's good that the integrator actually does some system tests, put up some test antennas, with the radios that you plan to deploy, and check how it performs, because every mine tunnel is different. But the values that we have used in both examples, I would say, is a little bit on the conservative side. But indicative of some kind of an average that we have experienced. Good.
Just something to add to what Stephen is saying, we have found that even along doglegs, you would find that the signal propagates pretty well. But as he quite rightly said, it depends also, of course, very much on the type of tunnel, the type of surfaces, and the dimensions, ceiling versus width of the tunnel.
Yes, but in our case studies, you'll get some examples of what our customers have done, and it's quite interesting to just see what the performance is actually. Okay, Ernst, if you can take this slide.
Yes, thank you, Stephen. So this is just to put it into perspective, this is an example, a case study we did for a customer that wanted to deploy our Healy antennas within a train tunnel. Now, the cross-section of the tunnel was around about 5 meters, and we measured the receiver at 800 meters. And this was done with specifically with our own design simulation software. And we did a few rough calculations at 2.4 and 5.5 gigahertz. And we did two different calculations and measured the antenna against the wall, exactly against the wall, and 0.5 meters from the wall. So this is just to give the customer an idea of where the placement of the antenna should be and how that affects the performance of the antenna. As you can see here on the heat maps of the two different frequencies, at 2.4 gigahertz, you have against the wall. You can see it's quite concentrated on the sides at 2.4 gigs, and there's a lot of blue area, which is where there's no signal, where there's very low signal. And if you just move the antenna 0.5 meters from the wall, you can see it improves somewhat. But looking at 5.8 gigs, you can see that heat map that the distribution of the antenna waves are much better against the wall compared to 2.4 gigs, but there's still a few dead spots on the signal. But if you move the antenna just 0.5 meters from the wall at 5.8 gigs, you can see that the coverage is much better in the tunnel, and that you will be more likely to receive the transmitter at 800 meters down the tunnel when the antenna is not placed exactly against the wall. And we will discuss that just a few slides on, as this is detrimental to the placement of the antenna as well as the performance, as you can see here.
Yes, and it's just something I want to mention here that's quite interesting is that the red areas, I think, is about a 3 dB drop on the normal free space loss distance, and the blue areas is about a 20 dB drop of the signal. So if you calculate the link budget on that, you'll see that there's about a 20 dB fluctuation depending on the cross section of the tunnel. So where you are at that specific moment. But saying that this was simulated at 800 meters, and it was using our bidirectional antenna. But this was just measured obviously in the one direction, and so you can replicate that to both sides. So it can be 800 to the one side and 800 to the other side. This tunnel was quite not a very wide tunnel. It was quite a thin tunnel, and it was concrete sides. So just to show you that. And then another thing that I think is important to show you in this slide is that if you mount your antennas 0.5 meters from the wall, as per this example over here, and you have 2.4 gigahertz, and you also have 5.8, for example, what happens is you have different hotspots within the tunnel than what you have over here. And this creates some kind of diversity, so that if you have a dual frequency scenario, that if you were at the 2.4 at that point over here, and you also have 5.8, then you'll see over here that your probability of having a better signal just improves so much. And that's why we promote dual band circular polarized antennas so often. It just makes sense. It gives you a much stable and much more reliable link down the tunnel. Good. So this is just on that same topic about diversity and MIMO. So this is just to show you that on our Heli 22 and 21 products, our antennas center to center is spaced around about 37, sorry, that's not millimeters, that's centimeters actually, which is about 15 inches. And you'll see on this table over here that if we take the wavelength of these frequencies at 2.4, it's about 37 centimeters. So you'll see that this antenna was designed, or at least the spacing between the antennas was designed to be 3 wavelengths, which is quite a good, we recommend it as a minimum distance between the antennas for to enhance your diversity and your MIMO within the tunnel. And then if you look at 5.8 at these distances over here, we're getting about 6-7 times the wavelengths, which provides quite a good diversity spacing. So that's just this example over here. So looking at our recommendation, a minimum of 3 wavelengths, there's no right and wrong answer. If it can be more than that, it's also good if it's less than that, and that's all that you have to install the antenna. It will affect your diversity and MIMO slightly, or not just slightly, but depends how far or how close you actually mount these antennas. So it's just something to take into account when mounting. It's obviously, as per this example over here, better to space them even farther away. Just a minimum wavelength over here. It's again just a rule of thumb and a recommendation. But with our antennas, if you mount them directly against the wall, see over here that the bracket over here is about 120 millimeters, which means that you can mount this antenna directly to the wall. As long as the wall and metal parts are not touching this radome over here, it is perfectly fine. However, 1 wavelength minimum from the wall would be a more ideal situation. So somewhere between this scenario and somewhere between that scenario is perfectly good for implementation of these antennas. Good. So just to show you that historically, when we didn't really have MIMO as a common feature on different radios and routers and so on, you'd have, for example, a circular polarized antenna working from heli to heli. And over there, it's quite important to actually have, if you have a right-hand circular polarized antenna, to have on the other end also a right-hand circular polarized antenna. However, I'm going to contradict myself now. When you have a reflection off the wall, as I mentioned to you, if you transmit right hand over here, that reflection becomes a mirror image, and then you start getting left-hand circular polarized. So right hand is clockwise, so your signal rotates clockwise, and left hand rotates anti-clockwise. So although that will also be received by the receive antenna, because it is decorrelated, it will be a lower receive level. The same as taking a television antenna, as I mentioned, and the broadcasting corporation is transmitting vertical and you receive linear. Then you will receive the signal because of reflections, because of other factors, but it will be at a lower level. And you'd also experience some level of fluctuation, fading, and so on. So in that scenario over there, later MIMO became available. And as you can see over there, you can have completely decorrelated signals. But the nice thing about having left-hand and right-hand circular polarized antennas is when this reflects off the wall, you'll see over there that you will still benefit from the diversity antenna. So maybe your line of sight is to this antenna, or you don't have any line of sight, but its reflections would be completely in polarization with the left-hand circular polarized antenna, as in this example. So It just, for us, we always recommend having both right and left circular polarized antennas in various tunnels, mine tunnels, automotive tunnels, and so on. Good. So this is just a quick slide just to show you that there are some building blocks when it comes to diversity enhancement. So we, in a tunnel, in any type of industrial application, whether it is industrial IoT or LoRa or whatever the technology is used, the very first thing that one can consider is circular polarization. It actually becomes the building block or the foundation of the enhancement of diversity. So in other words, reducing fading, because you want to reduce fading to strengthen your link. The second part to that is actually your spatial diversity, having two different antennas. Even if it's two right-hand circular polarized antennas, having two different antennas becomes the next step in the building blocks. Having diverse frequencies, and I'll show you that shortly, that having a 2.4 and 5 gigs as an example, or if you use LTE to have 1.7 gigs plus 2.7 or whatever the other frequency band is together, actually makes quite a lot of sense because they just behave differently in the different tunnels. And then the apex is to have left and right circular polarization, as I mentioned to you on the previous slide. Good, some case studies and examples. This specific example over here is on our website, on our case studies, if you want to go and refer to that with a little bit more text and so on. But just to show you, this was a tunnel in South Africa that Peter and I attended that personally. And we were with a customer and an access point, actually a mesh provider, and some tests that were performed in the tunnel. So you'll see over here that we performed two tests over here. In this specific case, I can't remember if the existing access points that were deployed were mounted at 100 meters or 150 meters apart, but nevertheless, we performed a test in that same tunnel, and so I think the customer told us that the extent of the access point was about 150 meters, and then so they had to mount the access points actually 100 meters to make sure that there's some overlap between the different access points. This access point provider was actually utilizing antenna beam steering technology, which sounded like quite a nice feature. But when we performed our tests over here we did our first tests to a tablet and a phone. And this specific test over here was performed with our Heli 22. It was actually the predecessor of the Heli 22, which was a prototype antenna. And at 155 meters here, you can see that the 5 gigahertz signal over here, we were able to get minus 60 RSSI on the tests. With the 2.4 was slightly weaker on this one at minus 65 more or less, and this actually quite impressed the customer quite a lot. We repeated the test. We went further down the tunnel. And this was after an elbow or a bend in the tunnel. So this was after the first bend. You'll see over here at 200 meters the signal attenuated slightly, the same as with the 5 gigs and the 2.4. Then we performed a second set of tests, as you can see over here. The first one was well, these were both Heli to Heli tests. So in other words, this was set up as an access point to a device. In access mode. This one was more in a battle mesh type of scenario where we had Heli to Heli at 275 meters, Heli to Heli. So remember, this is Heli to linear antenna. This is Heli to Heli antenna, which is circular to circular antenna. So yeah, unfortunately, we didn't have additional let's say 5 gigahertz antennas. We only had our 2.4 and therefore only these tests. You'll see over here that at 275 meters in this platinum mine, we were getting -50 received by the mesh node. In the tunnel, we had a locomotive actually passing us. The tunnel was about 2.5, 3 meters by 2.5, 3 meters, which is quite a narrow tunnel. And as the locomotive passed, I actually had to step backwards to place myself against the wall so that it wouldn't be a health and safety risk for the locomotive. And you'll see with that locomotive passing and almost filling up most of the tunnel space, so becoming a major RF obstacle within that tunnel. The 2.4 gig signal deteriorated with about 10 dB. And if you can see over here, -60 still with this whole locomotive covering most of the tunnel was quite impressive. Our ping times went from about 2 milliseconds to actually 3 milliseconds, which was quite impressive as well. And you can also see that the throughput wasn't really affected through this whole scenario of the tests. Good. So this test, I was personally involved. This one, actually, the customer shared the results with us. I was not involved. This was a coal mine. They were not using intrinsically safe antennas, although we do supply intrinsically safe antennas, but this was within the safe zone. And yeah, you can see a completely different scenario, which is quite interesting. This was mesh node to mesh node, so the same as this scenario over here. And what they performed tests every 100 meters. So the first 100 meters, they had line of sight. After 200 meters, the tunnel had upwards and downwards inclines. So line of sight was completely lost. But you'll see here, quite interestingly, that 2.4 gigs, fantastic signal levels over here, did tests at 100, 200, 300, 400, 500, and then they got a little bit impatient and went through to 670 and 1 kilometer actually down this tunnel. So in this case over here, you'll see that the signal level, even at 1 kilometer, was still -50 or just -50 to -60 actually. So it's phenomenal results at 500 meters. So this is over here, it was still in the -60s. So on the 5 gigahertz band, you'll see the ping times at the bottom with the throughputs that were achieved. So even up to 670 meters, they were getting fantastic results. The link was still quite a solid link, even at 1 kilometer. So although these results are achievable, it's obvious that you wouldn't always want to push your system to these extravagant limits. It's the same as my vehicle. I wouldn't, because the rev counter says I can do 8,000 RPM on it. It doesn't mean I should be taking it to 8,000 RPM. But this is just to show you what is possible. Good.
Stephen, maybe
just yes.
Just to add to what you were saying on that previous slide, I've also conducted tests using LTE at 2.3 gig. And the requirement from the customer, in this case, this was also a hard rock tunnel. And we had an LTE CPE placed 600 meters down the tunnel. The requirement was for voice over Wi-Fi. And we got the perfectly good enough signal to get very good voice over Wi-Fi to a recovery chamber 600 meters down the tunnel at 2.3 gig, as I say.
Good, thank you, Peter, for that input. So yes, our antennas have been used with LTE, with Wi-Fi, with mesh, and also with LoRa. Good. This was also in actually the first example in a platinum mine, and just to give you a little bit of an overview. So if you look at this, this was an active stope area where they were actively drilling on that day. On the surface over here. This was also a drilling surface, but if you look at the top over here, the team was actually, the mining team was actually actively drilling over here. And so we went with a mesh setup on the providing backhaul and access at each point. And this was a major incline over here. This was a tunnel, so we actually went mesh to mesh node over here and to this mesh node over here. And this mesh node was actually broadcasting inside this stope area. But just to put this a little bit in perspective, is that this little tunnel over here is, it was about 1.5 by 1.5 meters. So we didn't have to crawl through it, but I had to bend quite severely to get through that hole. So it was more like a hole in the wall rather than a tunnel. And just because it was a test and because we didn't want to do an installation inside, and because the miners were also very actively busy over there, we decided not to install the antennas on the inside, but actually on the outside, so radiating through this hole into this chamber. And so you can see the test results over here. Test 1, 2, 3, 4 in almost line of sight, but you can now imagine, for those who understand Fresnel zones, that this would be impacting your signal quite severely from a Fresnel zone perspective. And so we did test. So here are the results. This was the RSSI test. We couldn't do full tests over here because our time was limited in this chamber. And you'll see over here that we achieved -60s in this line of sight environment. But as soon as we moved over here, where they were drilling, we couldn't go right against this, the face because they were active. So we stood right behind the miners, and we performed tests over here 5, 6, and 7. And here's the results over there. So -70s, -80s RSSI at this point over here. But keeping in mind that this is a complete unideal situation because you're radiating through this little hole. If that antenna was placed inside, you'd cover this whole area fantastically. So with these results, the customer actually determined that it would be perfectly fine for them to change over from a manual labor-intensive drilling exercise to implement autonomous drilling as a result of these tests. Okay.
And just
next slide was
yes, is the distance. The distance there at the top you can see is 100 meters from end to end.
Okay, thank you. Then another example, this is a different customer. This is results provided by the customer to us, just as information, what he achieved. This was a gold mine, and the AP was implemented over here. This is just a sketch of the tunnels and just some test results that he's achieved. This was a 2x2 MIMO configuration. And he was using it as a voice over IP on a Wi-Fi access point. So this is a proprietary access point of the customer. But so these are the results of the tests. So you'll see here at 459 meters, some tests that he did, -59 dBm, and then right up to 660 meters, -70 dBm. So just to give you another example of a case study that's also on our website. This was that same customer using our Heli 3 antenna in a 2x2 MIMO configuration. Over here he was using voice over IP in also in a mesh configuration. You can see over here that this is the conveyor belt area. So the customer explained to me that this area is highly cluttered with metallic mesh, with metallic equipment, and it's from an RF perspective a very harsh environment. So the test results that the customer has given to me over here is that at 400 meters, 500, 600, and at 950 meters. So here's all the results. All this information is on our website if you'd like to get some more information on that. Good. So that's just these case studies are just to explain to you that it's not just talk. We actually have the results to show the performance of the antennas. Good. Ernst, this is where I hand over to you. Ilona, if you can
Yes,
just
thank you,
make
Stephen.
a presenter, that will be nice.
Just quickly, just a moment. Okay, thank you, Stephen, and I think you can take a sip of water now. And
Oh, thank you.
so this is just to wrap everything up. I'm just going to give a quick overview of the wide range of antennas Poynting has to offer for underground communication and mines. So let's begin with our normal Healy series. Now, our CEO, Dr. Andre Fourie, designed the original Healy series 15 years ago, and this antenna has been sold, our original Healy series has been sold for approximately 15 years, and they are still being used in the mines that they were deployed back then. And it didn't get a lot of traction back then because the technology wasn't available for the antennas yet. But over the past few years, we've seen a significant increase in sales and interest in our Healy series. And therefore, we revisited the design of our Healy antennas and redesigned it with a new tapered Healy design, which has now been patented. Now, what's the benefit of this tapered design? This tapered design gives us a wide bandwidth as well as an improved gain. That is why it allows us to cover the entire 5 to 6 gigahertz, 5 gigahertz band. And we also use the same design in our Healy 31, which operates from 1.7 all the way to 7.2 gigahertz. So this has drastically improved our performance with our Healy antennas, and yeah, we have seen a significant increase in sales with our mini Healy antenna range in deployments of mines. Now, just to give
if I can just make a comment over there, is that
yes,
so our normal Healy series is actually still selling very high volumes. As you mentioned over there, is that these have been on the market for more than 15 years. And the thing is, because they are so robust and because they are so dependable, and because people have been using them for all those years, we also haven't really seen any returns on these antennas. So I'm not sure, are they, if something is going faulty, are they just replacing it? But we haven't seen any returns on these antennas, which is quite interesting as well. So it seems like they are quite robust. And we've also had situations of mines with minor flooding and so on, and the antennas are still working perfectly fine after that. So there's quite a lot of merit in having a good thing. So we still continue to sell the Healy series, and we probably will carry on with it for the unforeseen future, just because they're so well known and because so many people use them currently. But with that, also the mini Healy series that we've launched recently is to be able to provide very wide band features, as Ernst mentioned, to provide a very constant gain over 1.7 to 7.2 gigs is quite a phenomenal achievement. And so to have that wide bandwidth, excellent VSWR and excellent gain over that whole band is quite good. So it becomes horses for horses again. So if one selects the Healy series antenna or the mini Healy series, they both form part of our 9-point antenna range. And as I mentioned, to be used in automotive, metro, rail, and mining tunnels, and fully suited for those environments. Sorry, Ernst, back to you.
No, thank you, Stephen. I appreciate the further explanation. So I just also want to give a quick rundown. This is our unidirectional mini Healy range. This is our Healy 11, 12, and 13, 2.4 and 5 gig dual band, and our unidirectional. And then after we have our bidirectional mini Healy range, which is our Healy 17, 18, and 19. And they're also 2.4 and 5 to 6 gig Wi-Fi dual band. And as Stephen mentioned before, here's our Healy 22. You have the normal roof brackets, roof mount, and then you have your roof bolt brackets, which can be used in the mining sector. And they are 2x2 MIMO, 2.4 and 5 gigahertz, and bidirectional. And then lastly, we just have our flagship Healy 31, as mentioned before. Now this one operates from 1.7 all the way to 7.2 gigahertz as mentioned, and covers all the popular technologies, even the Wi-Fi 6 and 5G or the 5G bands in the mines. Now this is just a quick cheat sheet for everyone if they want to know which antennas cover which bands. You can see here's our 2.4, only 2.4 is our Heli 11 and Heli 17. Our 5 to 6 gig antennas are Heli 12 and our Heli 18, which is unidirectional, bidirectional. And then our dual band 2.4 and 5 to 6 gigahertz is our Heli 13 for unidirectional and Heli 19 for the bidirectional. And yes, all our antennas are tested and standardized against the harsh environment of the mining industry. As we all know, it's a very rugged, and it requires a rugged technologies and equipment to operate down in a mine. So we test our antennas against all the various aspects, such as water ingress, where we implement gauze filters for pressure control as well as corrosion. That's why we use our stainless steel 316 stainless steel brackets, and as Steven mentioned, we do have intrinsically safe antennas, and all these are tested in-house and also certified by certified bodies. Now, just to give a quick, if you want, we also have our MIMO 3 antenna, which is an automotive antenna, but it can also be used in mines. It's a MIMO 4x4 MIMO LTE as well as dual band Wi-Fi 2.4 and 5E. So this can be used in the in the underground mines to help with automotive use, and it also has it's waterproof and dust-proof and with an IP68 rating. Now, if the MIMO 3 is a bit too large for you, we also have our puck range, which is quite a large range, but it's also it offers LTE and dual band Wi-Fi, and you can have a look at our product range on our website, and you can see the various options that are available. And both of these antennas are foam filled and IP68, so they can be mounted upside down, and you don't have to worry about any water ingress or impact damage against them. And lastly, we just have our brand new Rhino antenna range, which was launched a few weeks ago. At the top, we have our Omni 297, which is a wideband LTE antenna from 698 to 3.8 gigs. And it is also foam filled and IP68 rated. And then in February, we plan on launching a new Omni 700 series, which is going to be the same as our Rhino antenna, but it's going to offer 2.4 and 5 to 6 gigs Wi-Fi and a variety of combinations like either single band and dual band Wi-Fi. And yeah, it will be in our new rugged Rhino enclosure. And they will all come standard with a stainless steel L bracket, which can be used for pole and wall mounting. So yes, thank you all for your time. And yeah, over to you, Ilana.